So we have a graph here. The first thing we will do is do our Oyserga analysis. The origin is right here. So in the coordinate system, the Cartesian system, we're looking at something like that. Y-axis, velocity in normal units. X-axis is time in normal units. So we can easily read off the velocity in time from the graph. The slope would be dividing the axes, delta v over delta t, which is the acceleration. So any questions about acceleration? And so we could then see that the acceleration of this one is 0. Then it undergoes a negative acceleration, and then the acceleration is 0. Similarly, we have no acceleration, then a positive acceleration, and 0 acceleration again. The area, v times t, is the change in position, delta x. So we've done our analysis here. Now, so we have, from the scenario, reading the prompt, we have x traveling across a horizontal surface. Now, we can see x, which is the black dot, has a positive velocity. So it's moving in this direction. This velocity is a positive 4. And it collides with y. Now, y, we can see has a negative 2 velocity. So y has a negative velocity. And we've got a before, during, and after situation with the collision. They both have a mass of 2 kilograms. The momentum of the system and the kinetic energy of the system. All right, so when we look at the choices we're being given here, we're being asked if the momentum is conserved, whether the momentum is conserved and the kinetic energy is conserved. Now, there is a law, the law of conservation of linear momentum, and it is always conserved. So momentum conserved, momentum conserved. Momentum not conserved, momentum not conserved. That's never a possibility. Momentum is always conserved. Momentum is always conserved. We just know that conceptually. Now, we might infer from this picture, and it says during and after a collision. So after a collision, they both have the same positive velocity. So just on the face of it, it looks like they stick together. And since they stick together, we expect that we call this an inelastic collision because kinetic energy is not conserved. Kinetic energy is not conserved. We're looking at this one. So that's why this should be the right answer. Now we could go through and systematically prove whether this is the case. So beforehand here we have a mass of 2 kilograms times 4. So this is 8. And this one is minus 4. So that means beforehand the momentum of the system is 4 kilogram meters per second. Now afterward we have a velocity of 1. So we have 2 times 1, which is 2 kilogram meters per second, taken twice. So the momentum is 4 kilogram meters per second. There's 2 bodies, each with a 2 kilogram meters per second momentum. So we just showed that the momentum is conserved. So it has to be momentum is conserved. And of course, it's sticky. Now we can go through and we can calculate the kinetic energy to see if it's conserved. The kinetic energy, 1/2 mv squared. The mass being 2. And the velocity is 4. So that gives us 16 joules. And down here we have 1/2 mv squared. So 1/2 of 2 times the velocity of minus 2 gives us 4 joules. So we have a total of 20 joules beforehand. Now afterward, we have the kinetic energy of the first one, which is 1/2 2 times v squared, which is 1 squared. So we have 1 joule. And for the other one, that is exactly the same, we have 1 joule. So we have 20 joules becoming 2 joules. Kinetic energy is not constant. It's not conserved.